So our last video in the housing unit, specifically talking about linear prediction models, is to look at combining models, because we've made models so far trying to predict the selling price of a house from its number of square feet, number of bedrooms, number of bathrooms, and its lot size. We thought lot size wasn't very good, but maybe we want to combine two of the others that look like they will work. So far, we found that adding 1 square foot to a house increases the predicted selling price by $87.93, so that's per square foot. And adding a bedroom to a house increases the predicted selling price by $76,425. So you might look at it this way. Suppose you have a house, 1,500 square feet, 2 bedrooms, it's sold for $380,000. You have another house, 1,600 square feet, 3 bedrooms, and you want to know how much should we predict that house's selling price will increase by. And you think, okay, well, we know how square feet and selling price are related. We know how bedrooms and selling price are related. So you think, let's combine these. So you make an argument like this. House 2 is 100 more square feet, so it's predicted to sell for $8,793 more. 100 square feet bigger times 8793 gives you $8,793. And it's one additional bedroom, so 1 times 76425 gives you this. So then you might add those two together and get $85,218 as your predicted selling price for house 2. Well, does that work? And the answer is unfortunately no, because the size of a house and its number of bedrooms are not what we call independent. That is, larger houses are just more likely to have more bedrooms, and houses with more bedrooms are likely to be larger. So the levels of these variables are kind of entangled in each other. If you try to predict the selling price of a house based on its size, unfortunately, you're kind of including number of bedrooms there a little bit sort of behind the scenes. You could say they have some covariance maybe, but we don't really get into words like that. In this class, you just think, well, they're correlated, the number of bedrooms and the house size. And the same thing goes with the number of bathrooms. So realistically, though, when you're looking at predicting prices of things like housing, if you noticed on Zillow.com, they have estimated selling prices, and those are usually very, very close. So how do they do it? Well, they take all the variables into account using a similar but different method. There's one built into Excel where it's the same thing we just did, but it has multiple inputs. So we can't make a scatter plot because we have several different X variables. But you can look at the output. You don't need to know how to do this. It gets pretty technical, but the point is you basically just put in Excel that you want to use these 3 different predictor variables, bedrooms, bathrooms, and number of square feet to predict the price, and it gives you this whole mess of output. You'll look at a little bit of this if you take stats 2, but realistically, this is what matters, the coefficients of the intercept, bedrooms, bathrooms, and size per square feet. So if I put the model together like this, the equation would tell me my predicted selling price is $351,127. So again, that's the intercept amount. So if there were 0 bedrooms, 0 bathrooms, and 0 square feet, that would be your predicted selling price, which again doesn't necessarily make a lot of sense, but that's what the math works out to. This model tells you that each bedroom increases the predicted selling price by $67,090, which is a little bit less than our previous one. It tells you that each additional bathroom actually lowers the predicted selling price by $27,000, which again doesn't make a lot of sense. Adding a bathroom should not reduce the selling price. And this one says that each additional square feet, if you have the same number of bedrooms and bathrooms, only increases the price by $2.04 per square foot, which is quite a bit lower than we saw before. So the thing is, this is not a particularly good equation. I would not advise anyone to use this. For one, the number of bathrooms coefficient doesn't make any sense, but also, this says we have 16 observations. Well, we really had 15 because remember I deleted that one outlier. So you can't really make a good model out of 15 observations. To make a good one, you need hundreds at the minimum, probably thousands, tens of thousands, hundreds of thousands. And then you need to look at every single possible variable. So when we see a house in our data set, like one of them where the selling price was, which one was it? This one, where the selling price was way less than what was predicted, it's probably because there's some variable there that wasn't being taken into account, like condition of the house or something like that. But prediction models are all around us. Netflix tries to predict what you're going to watch and unfortunately kind of shoves you into a bubble of things you're interested in. Same with Facebook. Twitter does it to a limited extent, but same with pretty much any prediction algorithm. They're trying to figure out, what are you going to be interested in, looking at all the data they have available. But of course, they don't know every single variable there is. And sometimes they can be really stupid. Like on Netflix, I've seen every episode of The Office like 10 times, but they still have it as a 57% match. I don't know why. Maybe I don't watch a lot of other workplace dramas. But that's the idea, is that prediction gets very complicated. This is sort of the simplest version you can do in this class, is just making a linear model. And, this works for some limited aspects. Mostly we rely on computing power to come up with junk like this that then we try to understand what it's doing. But as the models get more complicated, it's much tougher for humans even to figure out what's going on. But that's the basic idea. In this class, if you know how to do this and interpret and know how to calculate a correlation coefficient, and even this predicted price and the residuals, that is enough to make me really happy with your performance in Stats 1.